There are a couple of slides that were nominally in lecture 1, I think, that we've got to finish off today. And see if we can get this idea of phasor analysis. Quiet, please. Thank you. A cos omega t plus theta. We see every voltage or current in the circuit is going to look something like that for different values of A and theta. So let's suppose that's an input voltage. What if we pretend that it's this? Let's pretend that it's this instead. Analyse the circuit with this complex exponential rather than a sinusoid. Certainly we can do that, and we know the real part of AE to the j omega t plus theta, the real part of it is our actual input. So what we can do is we can analyse a circuit with that input, do everything we want, get voltages and currents, and just take the real part to get the actual current or voltage waveform. Okay. So you might say, why would we do it? But it's going to turn out that it's easier to deal with these quantities. It turns trigonometry, if we've got these, tracking those around the circuit, it's trigonometry. If we track complex exponentials, it's complex arithmetic. So it's a little bit easier to do the analysis with complex numbers. The other thing is to note that this bit here, we don't really need to keep track of, because it's the same for every part of the circuit. The frequency's not changing. Every current, every voltage will have that e to the j omega t part, and it's only the amplitudes and phases that change. Therefore, we don't need to keep the e to the j omega t in every term. We just get rid of it. And what we get left with is a thing called a phasor. That's notation for a e to the j theta. It's the complex number with amplitude A and phase theta, plus or minus theta. Should really write plus or minus there. So we drop an amplitude and phase is all we need to keep track of everywhere. So let's just keep track of that. So our voltages and currents are going to be these complex numbers. Let's see if I've said this thing here right, please. That's called the phasor, and this thing is called phasor analysis. And we're going to deal with tracking those quantities through its thing. So this is actual, pretend it's this, and then the phasor. So let's do an example, the same example that we started with, or we did at some point during last lecture, but where that is V M e to the j omega t. So let's make it the complex exponential version of it, Vm e to the j omega t. We can still just do our circuit analysis exactly as before, solve a differential equation, but we'll do it with this complex exponential instead of cosines in there. So if I do that, it's not that. Like last time, it's Vm e to the j omega t. And hopefully you do know that if I take the real part of that, I get my actual input, Vm cos omega t, by Euler's formula. So by Kirchhoff's voltage law, we'll do as we did last time, by Kirchhoff's voltage law, minus Vm e to the j omega t plus I times R, the voltage drop across the resistor, plus L times di by dt, the voltage drop across the inductor, equals 0. Kirchhoff's voltage law around that loop. Rearranging the derivative of current with respect to time plus 1 on L on R I equals Vm on L e to the j omega t. Now for the special case you might remember we looked at was, just to simplify it a little bit, Vm was 1 volt, R is 1 ohm and L is 1 Henry. So if I substitute that in, I get di dt plus I equals e to the j omega t. And we solved that one last time where instead of e to the j omega t here, I had cos omega t. Now I've got e to the j omega t. So really I'm just convincing you that this is going to work, that we get the same answer. So I'll just rewrite that. That's the differential equation to solve. The steady state solution, so ignoring the transient, steady state solution will be I equals some complex exponential, Im e to the j omega t plus some angle theta. So that will be the steady state solution for some Im and for some theta. It's what the form the current must be. Let's check that out. Let's take the derivative. Just as we did last time, but we had cosines, now complex exponentials. The derivative of this with respect to time will be what? What's outside the t? J omega is, so that's what comes down. So it'll be j omega times Im e to the j omega t plus theta. Last time we had cos, we differentiated it and we got sine or minus sine, whatever it was. Now I get j omega times the current itself. So if I plug that back up into the top, take that, plug it back up into there, what's my equation? Well, I get j omega times Im e to the j omega t plus theta plus the current itself. So in fact I get 1 plus j omega Im e to the j omega t plus theta equals the right hand side e to the j omega t. That's what I must satisfy. I have to find Im and theta, and they satisfy that equation. What do you notice about the e to the j omega t's? What can I do? I just cancel. There's an e to the j omega t on that side and e to the j omega t on that side. They cancel out. I get left with 1 plus j omega I m e to the j theta equals 1. This is the phasor. You know, we said we don't need to keep track of the e to the j omega t's because they cancel out everywhere. That's the example of it for this case. It's going to be the same in every term, everywhere. So they'll always cancel out. All I have to really worry about is this Im e to the j theta, and that is the phasor for the current. I have to solve that equation. So I'll rewrite it so we know where we're up to. Okay, shut up! I've got a complex number equals a complex number. I can match the real parts, match the imaginary parts, or I could match the amplitudes and the phasors. And so here I've got one. They're not in the right forms to directly match. So let's see. Let's note that I'm going to try to put this in polar form. Do you call it polar form? Something e to the j theta? Is that what do you call that? Polar? Okay, good. Just make sure I use the same terminology. Rectangular for a plus jb? No. What terminology do you use? Cartesian form. Okay, so I'll try to use Cartesian. If I say rectangular, I mean Cartesian. I want to get that in polar form. So note that 1 plus j omega equals, what's that in polar form? Square root of 1 plus omega squared. A plus jb, the amplitude's the square root of a squared plus b squared. And the phase is what? Tan inverse omega. Just remember the little triangle there. This is 1, that's omega, so that's the radius, the amplitude, and that's the angle, theta. Tan inverse B on A or something, or the imaginary part on the real part. So if that's 1 plus j omega, hopefully you know what 1 on 1 plus j omega is. Yep? Okay, good. So therefore, Im e to the j theta must equal 1 on that, which is going to be 1 on the square root of 1 plus omega squared, e to the minus j tan inverse omega. So the amplitude's 1 on, and the phase, I take the negative of the phase. So what do I know? I know that Im is 1 on the square root of 1 plus omega squared, and I know that theta is minus tan inverse omega by matching the amplitudes and the phases of the two complex numbers. You can sort of find the parallel of every one of these steps when we had cosine there, and we had to match cos and sine, the coefficients of the coses and the sines, and then use cos A plus B equals cos A cos B minus sine A sine B. Trigonometric identities, complex arithmetic in this case instead. So if that's the case, what was I? Well, it was I, to get the actual complex exponential, I put the j omega t back in, which had cancelled out before. So we know that is 1 on the square root of 1 plus omega squared e to the j omega t minus tan inverse omega. The real waveform is the real part of that. This was with this complex exponential, but the actual input is the actual output current is the real part of that. So take the real part of I, and I will get 1 on the square root of 1 plus omega squared cos of omega t minus tan inverse omega, which is exactly what we got last time. So yes, at least in that case, this works. We can pretend it's a complex exponential input, do some complex arithmetic, circuit laws with these complex quantities, take the real part at the end, and we get the right answer. Now, the good news is, quiet please. The good news is you don't have to solve differential equations, plug them in every time and do it. What we're getting to is to be able to take a circuit, replace inductors by J times omega times L, replace capacitors by 1 on J omega C, and leave the resistors as R, and just do complex circuit analysis. Normal KVL, nodal analysis, mesh analysis, in the complex domain and we solve our circuits. That's the beauty of it. Once you've done this, you don't have to do differential equations at all. So you avoid it altogether. You're only interested in steady state behaviour. You just need complex arithmetic. Now, if complex arithmetic threw you there, that's okay. You need to brush up on it a little bit. There you go. If you don't get that, you need to brush up on your complex arithmetic. You don't have to think it's funny, you just have to get it. We've done this. This is just what we've done. Except here they leave VM, R and L as general parameters, whereas I set them all to 1 to make life easy. But you'll see the steps there match what we just did. So that and that ending in that. Hey, quiet! Thank you. We end in that, which is the more general version of the one we looked at. It's worth certainly stepping through. All right, now you can talk. I'll just show you this another ECSE application. This is a quadruped robot called Big Dog. Some of you may have seen. Well and truly worth a look. That is not two people in a suit. So hopefully when you look at something like this, you do think about how you would actually do it, what the technology would be required, how many sensors you have to have all over the place, accelerometers knowing exactly where you are, and the control systems to fix it up. It's quite a phenomenal quadruped robot. One too many tequilas there, I think. Now time for some dressage. There's Big Dog. Think of all the sensing and actuation that's going on there, all the control loops. Ridiculous. Okay. Someone did just give me a whole box of these favourites as well, so I forgot to ask you. Any questions you ask, you do get a chocolate today. So phasors, they're not high energy weapons from Star Trek, but it's a simple notation for sinusoids which are of the same frequency. An easy way to graphically compare sinusoids of different phases and magnitudes, and the basis for complex impedances to simplify circuit analysis when you have lots of capacitors and inductors. Gets rid of differential equations for you, this approach. I said the phasor is the complex number corresponding to the amplitude and the phase, AE to the J theta. We've sort of covered this. If we assumed a forcing function of the form Vme to the j omega t, a complex exponential, totally fabricated, but we can do it, then every steady state voltage or current will have the same form, but might have a different amplitude and a different phase. And so it's only the amplitude and phase we need to find. So we simply note the frequency, drop that factor because it's the same everywhere, and we're left with just the thing we need to worry about, which is Vm at angle theta. And so this, as I said, this notation, you sort of say Vm at angle theta. It's meant to be a little angle sign, but remember, it is the complex number Vm e to the j theta. That's what it means. Complex number Vm e to the j theta. So, let's say we have to convert the following voltage waveforms to their phasors. I'll do V1 and then I'll let you do V2 on melts. The question is asked. But V1, the phasor corresponding to this thing here, notice that it's cos and it's positive, so that's all right, it's a cos there. So that it is simply 12. I just read off the amplitude at angle minus 425 degrees. I could just write that, but maybe I want the angle between 0 and 360 rather than being bigger than 360. So I can add or subtract 360 degrees to the phase and it doesn't change anything. Go around the circle and just come back to the same spot. So that's the same as 12 at angle minus 425 degrees plus 360 degrees, which then equals 12 at angle minus 65 degrees. So that's the phasor corresponding to V1t, the time domain waveform V1t. In the phasor domain, it's represented by this complex number, 12e to the minus j 65 degrees. So the thing we need to be careful of, though, is it needs to be cos. Our reference is cosine. So when you do V2, you first need to change the sign to a cosine by changing the angle appropriately. And that's a Meltz question for you. Is it open? I just got kicked out. Thank you. Okay, 10, 9. What? You still had 8 seconds. You need more? By the way, the leaderboard is incredibly tight. Before this lecture, 3 people on 46. Another 1 or 2 on 45. Very tight at the top. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. So 54. Sorry, 54 out of 86 said C. 18 at angle minus 85.8, which is correct. I need to change it to cos, which I do by subtracting 90 degrees. Sine of x is cos of 90 minus x. Cos of x minus 90. Okay. Shush! So we need to be able to go take a cosine or a sine and convert it to phasor form. And the only catch is it has to be expressed as a cosine, not as a sine. The reference is cosine. Can you go the other way? Convert the following phasors to the time domain. I think it's V2 on melts. These ones aren't so tricky. So V2, do V2 on melts. I'll do V1. So in the time domain, V1 of t corresponding to that phasor is 10 cos omega t plus 20 degrees. The 10 tells me the amplitude, the 20 tells me the phase. It's for cos omega t. I don't know the omega, so I'll just write omega t. Question doesn't tell me the omega. You just need to do V2t. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. And nearly everybody shush! Now you can ask me a question. You can put up your hand and ask me a question, or shut up. Thank you. So 12 cos omega t minus 60, 90% of respondents had that. I showed you a big dog. I should show you a big cat. Same company. This one's the fastest robot quadruped known to mankind. It's not called Big Cat, it's called Wildcat. Same company. Not easy to make something run. Just warming up, a few stretches. don't actually know how fast it can run, but pretty fast. Oh! Was it maybe Google just bought this company? Can't remember. But. So what we have to do now is how do we treat resistors, capacitors and inductors in this phasor world? We know V equals I. We know the time domain relationships between voltage and current for resistors, capacitors and inductors, but what about phasors? So I could have, let's just get this right, some resistor there, time voltage, time domain current, and I know Ohm's law for it. But if that's a phasor voltage and a phasor current, how are they related? Because this is what I now need. If I'm going to do everything with phasors, if I put a phasor voltage on a resistor, what is the phasor current? What's Ohm's law in the phasor domain? And Ohm's, this one isn't that much different, right? Let's have a look. Let's suppose that my phasor V, I won't do that. Let's suppose that I put in a complex exponential, Vm e to the j omega t plus theta V, and I'm going to put in say that the current is another complex exponential with some different amplitude and phase. What do I know? I know Ohm's law. So I know in the time domain that V equals Ri. Therefore, I know Vm e to the j omega t plus theta V equals R times Im e to the j omega t plus theta I. I can get rid of the e to the j omega t's, they cancel from both sides, because that leaves me my phasor voltage. Vm e to the j theta V equals R times Im e to the j theta I, cancelling out the e to the j omega t from both sides. But what is Vm e to the j omega theta V? That's my phasor V, and it equals R times that, which is my phasor current. So V equals Ri, whether I'm in the time domain or I'm in the phasor domain. Now, if I only had resistors, I don't need all this phasor stuff. That's the point, because V equals Ri. It's because of capacitors and inductors that I need it, but for completeness, this is what we can do. If I put a phasor voltage and I'm only dealing in that domain, V equals Ri. What does that mean? Well, the voltage and the current waveforms are in phase. They're in the same direction. Resistors don't introduce any phase changes between voltage and current. Inductors and capacitors do. But resistors, well, it doesn't do anything. V just scales the current. They're aligned in terms of the phases. That could be I, that could be V. They're in phase, meaning the maximums occur at the same time. So that's what I've said. Now this example will seem a bit silly because you could do it instantaneously without phasors. But we'll just work through to show you the way to do it in the phasor domain. I'm told Vt up here as a time domain signal. And I put it through a 6 ohm resistor and I want to find the current. Of course you can tell me instantaneously what it is from Ohm's law in the time domain. But let's do it in the phasor domain. The phasor V corresponding to the underlying voltage is 24 at angle 75 degrees. And I know that V equals Ri in the phasor domain, so the phasor current is 24 at angle 75 degrees divided by 6 ohms, which is 4 at angle 75 degree amps. So that's my phasor current, but if I want it in the time domain, I do the other conversion. Therefore, in the time domain, I of t will equal 4 cos 377t plus 75 degrees. Well, of course, that's just Vt divided by 6, because I could just do Ohm's law in the time domain directly. When we do it for inductors and capacitors, it's going to be different. We won't have to differentiate. We won't have to integrate. But for completeness, that's how we do it for resistors. Another entry from last semester, I think. Some of the faces are a little bit different, but they were the tutors in that semester. And another entry there. If Photoshop is involved, it seems to go very well. And the sillier you make me and John look, the better, I think. Let's follow exactly the procedure we just did for resistors, but for inductors now. This is the time domain up the top. Phasor domain here. I know in the time domain that V equals L times di by dt. What does that mean in the phasor domain? It's going to be simpler. So again, I put in the phasor voltage and I have some phasor current, and I want to see how they're related. Sorry, this is complex exponential in the time domain, not phasor. If that's my V and my I, how are they related? V equals L times di by dt. So I plug them both in. Plug that there, and I plug this in for I. So the relationship must be Vm e to the j omega t plus theta v equals L times the derivative of Im e to the j omega, which is j omega, times Im e to the j omega t plus theta I. That's the derivative with respect to time of the current. The j omega comes down out the front. I cancel out the omega t's again, the e to the j omega t's. So Vm e to the j theta v equals j omega L Im e to the j theta I. Phasor voltage is j times omega times L times phasor current. I've got an Ohm's law for inductors now. A simple linear relationship between, if you like, between phasor voltage and phasor current. V equals j omega Li No need to differentiate. It's all captured in this relationship between the phasor voltage and current. It looks like Ohm's law, but what's the equivalent of resistance for an inductor? J times omega times L. It's called the impedance. The impedance of an inductor, J omega L, and it's frequency dependent. That's what we wanted. This was the property. The resistor is just R no matter what frequency. The inductor changes with frequency. Its effect is frequency dependent. So if we plot voltage and current waveforms, you'll see that the voltage in this case, this one here, is leading the current by 90 degrees. The voltage is leading the current by 90 degrees. If that's the current, rotate 90 degrees to get the voltage. Why is that? Well, remember V equals J omega L times I. If you multiply by J, what's that equivalent to? Well, remember that J equals e to the J 90 degrees. The thing's straight up on the complex plane, amplitude 1, angle 90. If I multiply something by e to the J 90, I've just rotated it anti-clockwise by 90 degrees. So that's why the voltage is now leading the current by 90 degrees. It's further around the revolutions. So that's what that says, what we've just done. A little bit harder. There's your next melts question. Kind of like applying Ohm's law now, but in the phasor domain for an inductor. So you've first got to work out what the phasor voltage is. You know omega, you know L, so you should be able to work out the phasor current, because V equals J omega L times I. You know omega, you know L, you can work out the phasor voltage, find the phasor current, and then go back to the time domain. Like a chocolate? Not allergic to peanuts? No. Good. I don't think I can throw that far. Oh, surprisingly. Looks like I can. Looks like I can. Right again. Share them. Surely if you got 2 or 3, you should throw them back and share them. Surely. I've only got one for me. Come on. I'm going to have one. Oh. Shit. J's angle 90 degrees. One at angle 90 degrees. So can you see what I've done? You go, get the voltage in phasor form, 12 at angle 20. This version of Ohm's law, if you like, for inductors, tells me V equals J omega Li. So I is B on J omega L. Omega is 377, L is 20 millihenries. I better lock it before I write it down. Okay, 50 out of 84 have now calculated that that is approximately 1.59 at angle minus 70 degrees. But that's in the phasor domain, so I convert back to time domain. Now you could have got that using V equals L times di by dt directly. So I is the integral of voltage. You could have got it by, I being 1 on L times the integral of voltage or whatever. But here's quite a convenient way to do it. And the point is we're going to be able to basically take this approach when we have a circuit full of inductors and capacitors. Everywhere you see an inductor, replace it by J omega L. Everywhere you see a capacitor, we haven't done it yet, but you're going to replace it by 1 on J omega C. And resistors stay as the resistor value. And then you can do parallel combinations, series combinations, all that stuff, but they're complex, and that's the only thing that makes it more difficult, complex arithmetic. So we'll do capacitors and start analysing some circuits tomorrow. Thanks for listening.